Hello, and welcome back to the series. In this video, we'll be continuing on kind of what we've been working on, but differently, we'll be working on some different scenarios and kind of uniquely explaining what happens and creating a code which will help us later on to finish our part C and D videos. So with that being said, let's go ahead and get started. I've gone ahead and put in what we usually use, and I've added these two new things. Polynomial, numpy.polynomial, and scipy.signal.TransferFunction. We both know what a polynomial transfer function, but just to remind us what this looks like in Python, if we give this some values 1, 2, and 3, let's say, it returns in increasing exponents, 1 plus 2x plus 3x squared. So if I add two more, like 5 and 2, this would be 5x cubed and 2x to the fourth. So you can see that it is what comes out. And similarly, we can do something with this where we multiply two polynomials. Let's say just 2 and 3. We get these all multiplied out and finally get a value to the third exponent, right? So that's pretty cool, pretty nifty tool, you might say. And today we're going to be creating some functions that will create our polynomials into transfer functions, and similarly vice versa. And then what does a transfer function look like? Well, if we give it two values, let's use the similar, or let's do 2, 1, and then let's do 1, 2, and 3. You can see it simply puts them in their order that we gave them to into two separate arrays, right? Very simple. So with that being said, let's go ahead and start off with defining a function. Let's start off by creating turning a polynomial into a transfer function, right? So let's say poly to tf for a transfer function, and then what we're going to want in there obviously is tf, right? Or no, actually let's do transfer function to polynomial, right? Alright, and what we're going to want to return obviously is these two values. So I'm going to do polynomial of we're going to have polynomial of the first one. So transfer function is going to be split up. So we're going to want the tf dot numerator to pull out the numerator, and then p the polynomial of tf dot denominator, right? So if we send that in and then we give a transfer function, let's call it tf1, simply give it, let's say 1, 2 and 3. And then for the second, we'll give it, just do 1 and 2. Nice and simple, right? So then if we call tf2 poly for polynomial and put in tf1 values, we should pull out the values. See? Amazing. That is what we're looking for. 1, 2, and 3, and then 1, 2, and the denominator. However, what we want to do is kind of swap these values. So what we want to do is very simple, actually. We're going to put the same things on both of these, and what we're going to do, obviously, go from the start to the end. So we put 2 semicolons from the start to the end, and then we're going to add a -1, which simply tells the code that we want to switch out the values. Alright, so if you do that for both and run this again, we should get inverse values. As you can see, we have 3, 2, and 1, and then 2 and 1 for the second. So perfect, that's what we're looking for. So we did the first part, transfer function to a polynomial. Now we want to do the second part where we want to transform a polynomial into a transfer function. So I'm going to call it poly to tf. And then obviously we're going to want a numerator and a denominator. Right? And then what we're going to return, transfer function, obviously. And we're going to return, we're returning the numerator. So we're going to do I'm going to call this d instead of m for denominator. So we'll call this n.coefficient to pull out the coefficient. And then d.coefficient to pull that one out. Then this should be 1f, I believe. And then if we run this again, call this now n and d for numerator and denominator. And then what do we need to do? Call polynomial, poly to tf, and put in the values n and d. Shift enter, we should get those values again. And beautiful. They're a little bit simplified, as you can see. But if you multiply all these values by 2, we should get the correct values, as 1.5 times 2 is 3, 1 times 2 is 2, 0.5 times 2 is 1, and so on. So that's amazing. We were able to switch these out and get 2 different equations, very simple. This is all we need for the first one, and this is all we need for the second one. All we want to do now is create a function that simply multiplies 2 transfer functions together, because that is something that we'll be needing later in this video and helping us out through our next 2 parts as well. So first off, I'm just going to create another transfer function, call it tf2. Then again, transfer function, but we are going to use some different values. Let's use 2 and 1, and then let's go 3, 1, 2, just to kind of throw it off and see how that works. So then I'm going to go up here, create a new function. Let's call it tf multiply. Multiplying 2 transfer functions, and then we're going to need a tf1 and a tf2, right? These 2 right here. I don't know why I just did that, but okay. And then we're going to want to return, but before that we want to get our numerators and denominators into separate things. So I'm going to call n1 d1 for the first one, and then n2 d2 for the second one, right? So what we're going to do is we have a transfer function, so I'm going to do a I think poly to tf for tf1, and then poly to tf for tf2 for the second one, right? And simply what we're going to want to return is them two separate, so n1 multiplied by n2, and then similarly for d, for the denominator, d1 times d2. This should be good. Now if we click shift enter, it should bring us all the way to a new values, and recall this now to see if it worked out. Multiply, but tf1 and tf2. So if we click shift enter in here, we had an issue. D, there's no D. I think this might not have to be this. I'm gonna mess this up. I think tf2 to poly is what we need. Let's try that out. See if that fixes the issue. Shift enter, shift enter. There we go. We see we get some weird numbers because it's still, we give it random values. If we go ahead and try to fix this up a little bit, see how it changes. There's just some clean numbers. But as you can see, it gives us our multiplied transfer function with our numerators and then our denominators, 2 separate arrays. So there we have it. There's our first step. Now, for our second step, we want to derive the expression for the transfer function of a PID controller, and we will be later create a code to generate that. So with that being said, let's go ahead and hop onto the whiteboard. Actually, before we head back and hop into this PID coding, I wanted to recall back here, I kind of wanted to change this up so that we can use it later on. We shouldn't have this polynomial up front. We forgot to turn this back into transfer function. So all we need to do is simply poly to TF, and we should get these cleaner values as we wanted. There we go. That's all we needed, and now we can hop into the PID controller. So hello, and welcome back to the whiteboard. I've gone ahead and run down our expression for our PID controller up ahead. So it's simply KC, which is our proportionality constant, multiplied by the error. In this case, we are dealing with the height of two tanks. So it's simply the specified height minus the actual, or the set point height minus the actual height of the reading. And then plus 1 over tau I times the, again, the error, but from the time 0 to t being the error time, with respect to time, obviously, plus tau d and multiplied by the derivative of the error with respect to time. So with that being said, let's go ahead and get started and kind of simplify this down according to Laplace transform that we know. So I can go ahead and erase this. As we know, this is E. I'm going to go ahead and simply write it out for our next equation. So we know that P is now equal to KC, still up front. And then this is our E now. And then we are adding 1 over tau I. That remains the same. And then we are multiplying it by derivative with respect to time. And what this is, thanks to Laplace transform, we know that this is simply going to be equal to the error E over our time dependent variable S. So this will be times E over S, right? And then for tau D times that, this is simply going to be plus tau D multiplied by E times S, right? And this is our new expression. Of course, this E is simply this error that we are trying to determine. Then we know that this is kind of all in this transfer function, so we can go ahead and pull that error out so that this is now equal to our constant KC multiplied by E, our error. And then we're going to have a 1 here now. And then this E is gone, so it's 1 over tau I multiplied by S. And then plus this E is gone, so it's simply tau D multiplied by S. Then now we can try to give it all a common denominator by simply multiplying it all out by tau I and S together. So if you multiply this out, we end up with is equal to KC multiplied by epsilon, or the error still out, right? Then now this becomes tau I S plus 1 plus tau ds squared multiplied by tau d I, right? Tau d multiplied by tau I multiplied by s squared. And all that is all over tau I times s, right? So there we have our expression. As you can see now, we have it all in terms of s squared, s, and no s. So we can go ahead and kind of clean this up. I'm going to erase the top of the whiteboard so that we can go ahead and kind of write this expression. And the increasing order or decreasing order, so that we can later plug it into our collaboratory code kind of easier, right? Makes it simpler for us later on. Okay, so now our new equation for our PID controller is, again, we're going to have KC. I'm going to keep this to the end, actually. And then the big equation, which we're going to have tau I s squared. And then we have, or tau I times tau d, actually. I almost lost that. Times tau d s squared. And we're going to have tau I plus s. Tau I times s, and then plus 1. All that is also going to be over tau I times s. And then again, this is all multiplied by e, our error, which is our difference between our height set point height and our actual height. So with that being said, let's go ahead and jump back into Python and kind of plot this, or plug this in, and see what values we get for our PID. Oh, welcome back to Collaboratory. I've gone ahead and put my whiteboard up here, so I have our final equation from our PID controller. So I can go ahead and create a new function now. I'm creating this whole block, or actually make it before multiply, because we might need it. Okay, so I'm going to do define PID controller. Let's make it all caps. Then we're just going to want a KC, obviously, a tau D, or tau I, and then a tau D. Right, that's all it needs. And then what we're going to want to return is the transfer function of these values. So first off, we have KC times tau dot, so KC times tau D multiplied by tau I. That's the first exponent, because it's s squared. Then it's s, we have KC times tau I. KC times tau I. And then we have plus 1, so simply KC, right? Should be good. And then for the second one, we simply just put a 0 and a 1, I believe. That's all we need. And then if we go ahead and put new values for our PID, put capitals, yep. Need 3 values. I'm going to say 1, 10 for tau I, and 1. What values do we get? And it looks like it's working. So all good on our PID controller. Now we can go ahead and work on the block diagram for a process under feedback control, deriving the corresponding servo transfer function, relating the control variable and the set point in terms of a controller, process, and measurement transfer functions, which we'll call GC, GP, and GM respectively. With that being said, let's go ahead and hop back on the whiteboard. So hello, and welcome back to the whiteboard. Now that we've gone ahead and done all those steps, let me kind of take you through this process and show you what we will be doing next. So first things first, we know that there's some process going on, right? So I'm going to make a little tank right here. Some process going in here. Call it process. Right, and we also know what the transfer function for this process looks like. We know that's simply R1, which is the resistance going into for this process, over A1, area multiplied by R1 S plus 1. Very simple, right? That is what we know about the process, and we know obviously that there is some QC that is going into it, and we know that it's leaving at a certain height, H1, right? And then before this hits the second tank, it goes through another small block, which we're going to say that it is simply 1 over R1. Right? And then this is what feeds the Q2 into the second process. Right? And we have our second process in here. And this kind of serves as a transformer for this idea. And in this second process, we have, similarly to the first one, we know that we can simply call it R2 over A2 multiplied by R2 multiplied by S, all plus 1. Right? And then we know that this whole process, then it pulls out this H2, the second height that we're curious about, right? And this is where the QC kind of comes in as well. This H2 also gets kind of recycled back into it, and before it does, it hits a measurement device, right? It hits this measurement device. Okay. And we know we're going to call it that it's simply being multiplied by plus 1, right? The value is going to be plus 1. Before that, it goes back and feeds the remaining H2. And this is where the QC comes in, is that there's a controller right here. Make it a little small, but this is the controller. Oops. Controller. And of course, before it goes into the controller, what goes into it, it's what we were talking about earlier, or E, or epsilon. Right? And why is that? Is because it comes from this proportionality, or not this proportionality, I was calling it, this, it pretty much counter, I think, I must be calling it wrong, but it pretty much just takes the difference between our set point, which we're feeding it, H2SP, and the H2 that is coming back from our measurement device. And that is where our epsilon comes in. That's what we used earlier to derive our PID control equation. Now that we have this and kind of understand the process a little better, we can go and simplify it a little bit more. What we can do is split this kind of into 3. We know that there's a process going on, right? And for what we were talking about earlier, like we said, we're going to use GC, GM, and GP. So for the process, we're going to call it GP. And this accounts not only the first process, but this entire transfer function, which we recall it as the forward process, this entirety here from QC all the way to H2. And that is kind of what we want to simplify. And going out of this process is H2, obviously. And from the process before is our controller, which is our GC, right? And then this gets recycled back into our GM for our measurement device. Then, of course, this back goes into the tester of the set point, which is the epsilon, or the difference between the set point and H2 coming back from this measurement device, H2. And H2 set point. Sweet. So now we can kind of work this around and get an equation for both our forward and backward process, right? So first of all, I kind of want to get the equation. What we want to do is kind of get what H2 is. So I'm going to write a generic equation right here, and then kind of erase this top one off the board and give us some more space to work on. So first off, like we said, we want to work for H2. And simply is going to be the difference between these two, right? These two values. So h2 sp for the set point minus h2. Then obviously we have to multiply it by gm, by our measurement device. Take that into account. However, for this case, we simplified it and made it a value of 1. Still important for our generic expression. And then it's multiplied by this forward process, right? We have to take into account about these transfer functions. So it's multiplied by GC and GP. GC and GP. Okay, so now I'm going to go ahead and erase the top of this and kind of work out this expression a little bit more. Hello, and welcome back to Collaboratory. So let's go ahead and put what we just worked on into our code. I'm actually going to delete a few of these cells that we do not need. PID. I think we don't need these anymore. Okay, now we can go ahead and continue on where we're just working on. So we want to create a transfer function for our Q1 to Q1 to H1 or Q1 to Q2, and then Q2 to H2, right? And so for Q1 and Q2, we're going to create a transfer function, and obviously we need two different things. Remember the numerator, we're just going to have 1, and then in the denominator, we're going to have A1 multiplied by R1, right? And then plus 1, right? And then similarly for our Q2 to H2, we have instead of 1, we have our R2, our resistance, in the numerator, and then in the denominator, we have similarly A2 multiplied by R2, and then plus 1 as well. So that's all we need. Obviously, A1, A2, and R2 don't have values, so let's go ahead and put those in. I'm going to make them very simple for this case just to see if it works. We're going to make A1 equal to 1, as well as A2, make that equal to 1 as well. And for R1 and R2, we'll make that equal to 2. R2 is equal to 2. So if we click Shift Enter and go ahead and recall our multiply function and multiply these two together. So we're going to do TF multiply, and we're going to multiply Q1, Q2, and Q2, H2. So that it gives us our total value for our process overall Q1 to Q2. There's values that it spits out. So I'm going to call this simply Q1 to H2, right? So that we can go ahead and use this in a new transfer function where we multiply this Q1 to H2, the whole process, by the PID control equation that we came up with up here. Right? So I'm going to make a new TF multiply, and as the first, I'm going to put recall the PID, so PID, and in there goes KC, tau I, and tau D. KC, tau I, and tau D. And that's for a first. And for a second, we're going to multiply by this Q1 H2. However, it's asking us values for KC, tau I, and tau D, obviously, because we haven't given it, inputted anything for it. So let's give it values. To make it very simple again, let's make it 1 for KC, tau I, let's say, let's give it 5, and then 0.1 for tau D. So if we go ahead and multiply this, we get this expression where we have in the numerator 0.1 s squared plus 0.05s plus 0.05 on the numerator, and then in the denominator we have s squared plus s plus 0.25. So now we can go ahead and call this our transfer function for our forward. So we can go ahead and use this later on, as that is what our forward transfer function would look like. So now we have that all set up. Let's go ahead and hop back on the whiteboard. Alright, now that I've freed up some space on the whiteboard, we can go ahead and continue on with this expression down here. What I'm going to do is simply multiply it out, multiply this GC, GP throughout this expression, so that we end up with H2 is now equal to H2 SP multiplied by GC, GP, GC, GP, minus H2 GM multiplied by this second part. So minus H2 GM GC GP. Alright. Why did I do that? So now that we can push this H2 second factor out to the left side and pack H2 together. So now we're at H2 plus H2 GM, this whole factor. So I'm just going to do H2. We're going to have 1 plus, plus this whole side. So plus GM, GC, GP is equal to H2 SP for a set point multiplied by GC, GP, and I forgot And then now we can go ahead and divide this side, or the right side, by this value 1 plus this whole multiplication of our three factors that we're taking into account to get our final value for H2. So H2 is now equal to H2 SP multiplied by GC multiplied by GP all over 1 plus GM multiplied by GC multiplied by GP. So there is our expression for H2. Now I'm going to go ahead and erase this out and kind of clear out a board, and then we can go on to our next step on determining our values for denominators, numerators, as well as the forward-backward process a little bit more in detail. Alright, looks good enough. Alright, I've gone ahead and put our expression that we just solved for up here at top right. And now what we can go ahead and do is kind of simplify even more by understanding what we do with GC, GP, GM, GP, and GC, how we compare these two. And it's actually quite simple. So what I'm going to do is kind of group this aside. We're going to have H2 is equal to H2 SP and have this whole factor of GC, GP over 1 plus GM, GP, GC as its own. So we're going to have, we're going to try to find out what GC, GP is and what GM is, right? And it's really simple. As we recall to our process, GC, GP is the controlling the process itself, so it's the forward reaction. So it's going to be equal in Laplace transform for what we're doing is in our forward numerator over our denominator for our forward reaction. And our GM is going to be the exact opposite. It's our reverse reaction or backwards. So it's going to be NB for numerator backwards and DB for denominator backwards. So now that we have those values, we can go ahead and plug those in back into here. And for now, I'm just going to have H2 equals H2 SP up here. And just imagine that we're bringing this all the way down throughout. But now I'm just going to be solving for that side and kind of simplifying it down a little bit. So if we go ahead and plug this in, this will have our numerator forward and denominator forward over 1 plus gm, which is numerator backwards over denominator backwards, multiplied by GCGP, because that's in our denominator as well. So NF and DF for numerator forward and denominator forward, right? Now we can kind of multiply this out, so we can start simplifying it a little bit, so that we have numerator forward over DF, which is all over 1 plus NB/NF over dBdF, yes. The two numerators and the two denominators and their positions. And now we can kind of continue simplifying simply by cross multiplying. Right. So we know that if we bring this out, NF, actually we can just simply start by crossing out. I don't know why I didn't do that before. We know that NF is the numerator both times and the denominator both times, so we can go ahead and multiply that out, so that we're left with 1 plus NB dB. Or no, that's not right. Yeah, no, we don't want to do that. Apologize. That isn't what we want to do. We have NF and DF. Okay, we multiply this out, so we know what to multiply this one by, so that this becomes NF over DF all over dB multiplied by dF plus NB/NF. That is divided by dB/dF. So now that we can multiply this out and simplify even more. So I'm just gonna simply have NF over dF is multiplied by dB/dF over dB/dF plus NB/NF. Right? See that? So now we can cross out things we know. We see that dF is both numerator and denominator, right? And then NF looks like we only have it down there. So let's continue out. So we have NF dB over dB/dF plus NB/NF. I'm going to go erase this out, put this in the top left corner so we can continue on working this with more space. That looks right. Okay, so this is what we worked out to get. NF dB all over dB/dF. So dB is only in 1 and NF is only in 1. So this is actually the furthest we can get at the moment. We can't simplify this even more actually, as we have our NF multiplied dB, which is our numerator of a forward reaction multiplied by a denominator of a backwards reaction, all over dB/dF, which is our denominator backwards multiplied by a denominator forwards, plus NB/NF, which is our numerator backwards multiplied by our numerator forwards. So with that being said, we can go ahead and utilize these two expressions into our Python code and kind of see what that situation looks like and kind of work that out. So let's go ahead and jump into our collaboratory. So hello, and welcome back to our collaboratory code that we've been working on so far. So now that we've gone ahead and gotten this expression for our forward, we can go ahead and imply that. So we're going to go ahead and create a new function up here. Of course, I'm just going to say define. What are we going to call it? Say transfer function feedback. Let's call it feed for the feedback that we're going to get, and then obviously we're going to have two transfer functions, our forward and our backwards. What do I call this? So I'm going to call it tf_f for forward and tf_b for backwards. All right, and then obviously it's very similar to this equation that we made up here. We're going to have a numerator denominator for each individual transfer function to a polynomial. So we're going to have a numerator for a forward reaction and then a denominator for forward reaction as well. And then similarly for our backwards, we're going to have a numerator b for numerator backwards and denominator b for denominators backwards. Like I said, very similar to this expression, we're transferring the transfer function, so tf to poly for polynomial, and then we're going to input the transfer function forward. And the same for the backwards, except we're using the backwards expression. So tf_b, and then obviously we need to tell it what tf_b. And then obviously we need to tell it what we want to return, right? And again, we're going to want to return it in some sort of polynomial back to a transfer function, right? We're going to have in the numerator is numerator forward times our denominator backwards. So that's going to be numerator f multiplied by denominator b, right? That's our numerator, and then our denominator, this whole expression, which is, put another parentheses, denominator b, then b multiplied by the denominator forward, denominator f, and all that added to numerator backwards multiplied by the numerator forward, backwards multiplied by, numerator backwards multiplied by the numerator forwards. Okay, let's make sure this looks good. So in the numerator forwards multiplied denominator backwards multiplied denominator forwards plus, okay, that looks good. So press shift enter in that and go down here and create a new function using our forward that we used and our backwards that we found. So we're gonna call tf feedback, right? Tf feedback. And then for forward, we're going to put this expression that we just solved for before we were on the whiteboard. So call it TF forward. And then for the backwards reaction, it's simply going to be polynomial, right? It's only that multiplied by 1. So I think we just put poly to 2f because it's polynomial, poly to 2f, and we want to put no, that's not right. I think we just simply put 1 and 1, if I'm not right, and put that in the multiply. No, I'm pretty sure it's the poly to tf. Let's see what it kicks out for us then. Okay, yes. So it can't be poly to 2f. Because we're putting numerator and denominator. No, we don't want that. I think we just want a transfer function, right? I think if we just delete the poly 2, it should be good. There we go. So here are the values that we achieved for our numerators and our denominators for our feedback. comparing the forward and the backwards expression. And obviously if we change these numbers throughout, even here, if we change this A2, it affects the final values, as you can see, as well as affecting this KC tau I. If we make this twice as large, it changes up our values completely. So there you have it. That is the final part of this second part, and I'll see you in the next one. Welcome back to Collaboratory. Now that we've gone ahead and kind of seen and finished our code, we want to test it out a little bit and simulate it through and see how it works. So first of all, we're given a unique scenario where we want to test out some certain values for it and see if our outputs are what we're needed. Then we will be creating a step response for the transfer function with these given values. And then we want to simulate the response of the forward transfer function to a sinusoidal cosine error input of amplitude 1 and a frequency of 1 radians per second. And then we will superimpose, compare the plot to the H2 error over time. That being said, let's go ahead and get started with this first series. So we want to make sure that our A1, A2, and R1 and R2 are all set equal respectively. We can get rid of this. Don't need that. So we have our A1, A2 all equal to each other. I'm just going to make that to delete some code. So that's all good. Now our KC, tau I, and tau D. We want our KC to be equal to 1, tau D to be 0.8, and our tau I to be 0.8, and our tau D to be 0. So KC1, tau I believe is 0.8, and our tau D is 0, if I remember correctly. 1, 0.8, and 0, and then we want a GM to be 1, which is already the scenario. So if we go ahead and shift enter on all of these, we should get our variables. Beautiful. So this is the expression that we have now for the function. We have 0.5s plus 0.625 in the numerator, and then 1s cubed plus 1s squared plus 0.75s plus 0.625 in the denominator. So with that being said, we can go ahead and make this into our function. I'm going to call it TFB. And as we said, we wanted to simulate the step response of the transfer function. So let's go ahead and do that. All we need to do is tf.b and do our step function dot step. And there we go. We get a bunch of values, 2 arrays, with this first array being with respect to time, or over time, and then this being our values for our function, right? Or our H2. So that being said, we want to graph this out, right? We want to simulate the response for both the forward and transfer function. So let's go ahead and copy and paste our known expression. So we want a line space. We want to be from 0 to, let's say, 100. Then we want 500 points. We want our y. So this is where the t step comes in. We need to make sure that it knows that our t is our t-plot, I believe, or TFB. I think a t-plot. And we're going to call this, what do we call it? H2 and time. I just make it an underscore. Comma H2 is equal to this. Our y, so we only need 1. Our add scatter, x is our t-plot, our y is going to be our H2. And name, we don't need that for now. Sweet. Go ahead and copy and paste this up here. And we should get a plot for our backwards reaction, right? There we have it. Beautiful. So as you can see, we start off at 0, 0 perfectly, and it kind of fluctuates back and forth, kind of like a wave, either a sine or a cosine wave, or a plot, just kind of what it looks like. And then over time, it starts stabilizing at about 1. And at around 100, it looks like it's about to be stabilizing. So let's go ahead and mess with this a little bit, see how it reacts. One thing, let's see where it ends, right? If we add 50 seconds, should we get a stabilized? And you can see it looks a lot more stable, and it looks like at about 150 it's going to be a lot more flat compared to 100. So we can imagine that around 200 seconds that this will be fully stable, which is pretty good. Then if we add 1,000 points or multiply by 1,000, we'd see it's a lot more accurate as well and looking a lot more clean. We can see that its peak is at about 1.76. So that's pretty cool. And we can see that the lowest is 0.34 roughly for the height. So that's all we need to do for step function. This is what it looks like. And for our next and final step, we want to plot it with an amplitude of 1 and a frequency of 1 radians per second for the plot of H2 compared to the error. So let's go ahead and do that. So how might we simulate this, you might ask? Well, we're going to use this function called, I think it's sine.lsim for the simulation. I don't think it's sine. Let's see, what could we use? I think it's sig. There we go. Ooh, what did I just do? sig.lsim. And then we're going to need some parameters. So we're going to need the, what are we going to, TF forward. And then we're going to need a U and a T, which is going to be our E. And then I think our T plot, which we're actually going to call it T sim because we're going to be simulating it. And our E value is simply, I think, np.exponential of W multiplied by our simulation plot. And we need our value for W and T sim. I believe W was 1. And then our T simulation, T sim is equal to np.line space. And then again, we're going to do 0 to 100 and start off with 500 points. So I believe that's all we need. Let me check if that's right. GCP and GP in series, 1 and 1. H2 and error. Okay, I think these values don't look right. I think I messed up. This should be cosine. Okay, yeah, numbers look a little bit better. Yeah, perfect. Okay. Well, there's only one way to see if that's right, is to graph it. And like we said, here's similar situation. We only want to pull out the H2, right? So I'm going to do underscore H2 and underscore for the other two values. Shift enter, and then now we can go ahead and graph this out, right? So I'm going to copy and paste this. We already put this in. We'll make subplots. X value is our T sim. And our Y for our first one is going to be H2, and our second is E. And we're naming this output and input. Input. And we should be good. Let's check this out. And there we go. Wow, look at that. Amazing. So as you can see, we can better understand how these correspond with each other, right? they fluctuate almost perfectly in sync. Let's go ahead and decrease this down to 50. Can get a better perspective on this, and we can also plot more points. Let's try 5,000 just to get a cleaner graph. Let's go ahead and zoom in this first anchor. So you can see it looks almost perfectly as a sine and cosine graph, right? This input starting at 0, and then it goes to the max of 1, it seems like. Just under 1. Never reaches it, and then fluctuates down to negative 0.5, and it goes back and forth until I zoom out, forget. Okay, sorry about that. And it kind of stays constant after that first initial drop, and however the input, it remains the same. At time 1, it's at, or time is equal to 0, it's at 1, and it goes all the way down to negative 1 at about 3 seconds, 3.14, and then it goes back up to 1 and back and forth. So hopefully this video helped you guys in some sort of way. I enjoyed helping you guys along the way, and thank you for watching. I hope to see you guys in the next one. Bye-bye.